Okay. Hmm. Okay. Well, hopefully I'll be better by Thursday. I was going to share actually before we start. Let's see. Oops. Let's see. Yeah, you can. What I was going to say is that I posted a fifth practice exam. Um, on their modules. Basically, we are more or less done with everything that's not integration. Integration is actually what we were going to start today. So if maybe we'll finish it like by Thursday. But if you wait by the end of the week, I would say like maybe five or six of the problems you would be able um either five or six of the six problems on each practice exam you should be able to do. Um, but with what we have currently done so far, you can do four out of six, because on each practice exam there's one or two integral problems. So and that's kind of like the only thing that's left for us to kind of like discuss basically. But today we'll start integrals, um, and maybe on Thursday we would be able to do all of it. The last topic for the exam on integration is polar coordinates, which a little bit already from Calc 2, but we will do it in a slightly different way, the polar coordinates thing. Um, so yeah, like basically, but definitely by the end of the week, I would say like you should be able to do like 80-90% of the exam problems. Um, but that's why I was sharing first my screen here on Firefox. Because I posted, yeah, I think I posted it today. Like I posted like a fifth practice exam. So I mean that is honestly like I think enough material to kind of like get like a good sense of what to expect on the exam. As I said, like this exam usually is like the one where like um, students do the best. So it's more like trying to get as many points as you can on this one because it's kind of like the more traditional calc exam, like from all compared to the first one and the third one. The first one is not even like a calculus exam because it's mostly like vectors, lines, planes, and and the third one, the final, is like it just has like a lot of like different stuff that's going on. But if you look at, I also post, I forgot to do this, but I also post kind of like a list of like true false questions as well for you to look at. And I'll probably put one or two of those like on the exam, so you can take a look at that as well. Let me see. Let me share my iPad. Um, let's see. You can see my screen, right? My iPad screen. Just double checking. Or can you not? Oh, perfect. Good. So as I was saying, like because like this was very last minute because I wasn't feeling too great in the morning. I will record this class just in case, like someone couldn't come to the class. I'll share the video after we're done. Um, Let me just start telling you a little bit about what we're supposed to discuss today. Um, so basically, what we're going to talk about is like how to do integrals. So how to integrate functions. But now the idea is that the functions that we will integrate are functions of two variables. Okay, so we're going to integrate functions that depend on x and y, and just as before, you know, like it's always useful to just like start with like the calc 1 situation, right? So how did integration work in calc 1 and calc 2? So basically, here, uh, I think like that's a good question. Like I think the only thing that was left from that example, um, right, like the only thing that was left from that example, now that you bring it up, it was that once you have the points, you had to evaluate the function at each point, to just to determine which was the max and the mean. I'll just probably add it to the notes, like at the end of the class, so that you can refer to it. But it's just kind of like plugging like the 4 points. There was nothing really else that was left in the problem, but I'll add it to the previous class notes so that you can kind of like refer to it. Um, I also, I think my plan, kind of like last time as well, will be to, like next Tuesday, I'll kind of like lecture for half the class. I'll lecture for half the class so that like, like the other half, like kind of we do more like kind of like office hours type things. So, but every practice exam has a Lagrange multiplier problem. There will be a Lagrange multiplier problem on the exam for sure. That is kind of like a very common type problem. Definitely, like like so. But if you kind of like look at the ones on the practice exams, that is like a pretty good like sense of how to do those, what to expect, because there's like plenty of examples on that front, like from the practice exams. Now, well, the exam will have 5 problems, so it's one fewer than it will be one fewer problem than the practice exams, because each practice exam has 6. So most likely probably it will be only one problem about integration. um but like it may have 2 parts, where like you have to set it up in different ways, like the integral. So um but yeah, I would say like probably no more than one. Definitely not more than two. Like two is always like the max that we ask on the exam about integration. But probably since like now there are 5 instead of 6, um, I'll just do what you'll see on some of the practice exams, where it's like an integration problem, but I ask you to set it up like in polar coordinates and in Cartesian coordinates, so to kind of like test both things. So it would be more like for one, I would say. But one that counts kind of like for two, because it is asking about 2 things. That's how I would summarize it. Um, so what I was going to say about this, in Calc 1, like, by the way, we will only do kind of like definite integrals in this class, basically. Um, so how were like the definite integrals in Calc 1 supposed to work? By the way, do let me know. I'll be checking the chat. So do let me know if for whatever reason sometimes like the iPad stops like sharing, like freezes. So then let me know, because then I'll kind of like resuscitate it. But um so the idea in Calc 1, right, is that you had, well, actually let me draw it. Let me draw the function like this. Right. So you had a function of one variable, y equals f of x. And then if I gave you like an interval a, b, right? Well, the integral from a to b of the function, like the first way you think about it in Calc 1 is that it is kind of like the net area between the graph of the function and the x-axis, right? Um, Basically, I'm just saying like net area because as you remember, like if the graph happens to be above the x-axis, it like the area counts positive. So let me color that here. So here, like the area would count positive, and right, and then when the graph is underneath the x-axis, then the area counts negative. And that's already baked into the integral, right? So like the integral works that way. So it's not something that you kind of like have to do by hand, right? Like that already like operates in that way. Um, Now there is in practice like the way you would find the definite integrals, right? Is using the fundamental theorem of calculus, right? To find the value of a definite integral, you can use the fundamental theorem. And basically, what the fundamental theorem said is that just to do it very quickly for one, like a simple example, um, because you can like do this all the time. So I don't think I need to remind you too much about it. But if you wanted to integrate something like x squared from 1 to 3, you have to find like an antiderivative, right? Like so a function whose derivative is x squared, and like there's this power rule, which in this case you add 1 to the exponent, so you get x cubed over 3, right? Well, strictly speaking, you could also add like a constant of integration, but for a definite integral, that doesn't make play such a big role, right? Because you evaluate at the bounds, and so that always goes away. So, so this in this case, well, you just evaluate at 3. 3, you get 3 cubed over 3, and then you subtract what you get. You get at 1, so you get 1 cubed over 3, and well, that is what 9 minus 1/3. Right, so that is like, and there in calc, especially in calc 2, you learn a lot of different ways. In calc 2, you learn a lot of different ways for doing these integrals. The only thing that you have to remember for our purposes is like the u substitution. That's the only thing I would ask you to do. Like, I'm not going to ask you anything that uses integration by parts or like trigonometric integrals or like all of these weird ones. So like just to again give you like a quick example with the u sub, just to kind of make sure like we're all on the same page, right? Like if with the u sub, well, this is like a very simple one, right? But with the u sub, you do like a u substitution, like u equals x squared here, du equals 2x dx, right? And then here you have two options, right? Because you can change the bounds or keep them the same and then evaluate, but I'll just change the bounds. Um, so when x equals 2, u equals 4, right? And when x equals 4, u equals 16, right? And that gives you e to the u du, right? And that is easy to integrate because like the integral of e to the x or e to the u is just like the same exponential. So you get e to the u plus a constant again at 4 and 16. And let me see if I can fit all of these. And that would be your answer in this case. So again, that in terms of like integration techniques, I'll make a remark about this. But in terms of integration techniques, like the only one that you really have to remember for our purposes, like is the u substitution. So in fact, you'll see. And hopefully, maybe I'll get to do an example of that today. But if not, definitely on Thursday. Kind of like the bulk, the majority of the problems in these integral problems is setting up the bounds. That's what's going to be interesting for our context, which is very different from the Calc 1 situation, because in Calc 1, find it, like the bounds are just like the bounds of an interval. There's not really much to think about. But here in Calc 3, finding the bounds of integration is kind of like really like the most important part of the problem. So in fact, like sometimes like 75% of the problem is like just finding the bounds, and then like the remaining 25% is just like doing the integral. So like here, like doing the actual integral is not as important for us as finding the bounds of integration. And so that's why we're not kind of like testing too much for not really testing too much this thing about the like these different integration techniques, because that's not really where our priorities lie in this class. Now, what I was going to say, but by the way, sorry, is this so far so good? Any questions up to this point? Okay, so what I was going to say is that in practice, the way I was describing is how you would find the values for the integrals, right? Finding antiderivatives, but there is, the original. If you can like go down the rabbit hole, the original definition for an integral uses this Riemann sum idea, which you kind of pay lip service to them at some point. So I'll just kind of like remind you what's behind that, because again, I'll kind of like say something about that for our context as well. So let me see if I can show you that on GeoGebra. So the idea of a Riemann sum, the idea of a Riemann sum is just like that you had like it's just kind of like a way to approximate the graph of a function. So the area of the graph of the function. So the idea is that you don't know how to find if the shape is complicated. What you can do is like instead kind of like find. Actually, let me use a different one, because this is like a little bit too chaotic. I think it shows both of them. Sorry, this one is fun. Well, these ads are kind of fun as well. Right. So the idea is that if you had if you have the graph of a function, right? And again, just think that it's like a complicated graph. If you wanted to approximate the area of the graph, um, what you can do is like instead find the areas of rectangles, and as you make the rectangles like thinner, right? Sorry, let's just put it here. Ooh, okay. Right, if you can see it here, as you make the rectangles thinner, right, like there's almost no difference between the area of the graph and the area of these rectangles. I'll take a picture for one of these where it's a little bit more obvious that there's some gap. uh, right. um, so the way the integral is actually defined, it is through these Riemann sums. And that is like an important idea, just because in practice, like maybe it's not something you can really kind of like appreciate when you're just taking Calc 1 and Calc 2, but you kind of get a sense that doing integrals is actually much harder than doing derivatives. Finding the value of an integral is a much more complicated problem than finding the value of a derivative. And so if you have like crazy functions, or like ones for which an antiderivative is not known, actually, like like the numerical methods that you would use on a computer, that this is how they actually find an approximation for the value of the integral. So that is like the main reason why this idea is important, because like it is used in practice a lot when you're dealing with like actual concrete real world like problems where like finding an antiderivative is not super clear. And that will be useful in a moment when I tell you about the double integrals in as well. So let me just put this here. So again, I'll just make a comment about this that the way the integral is defined in Calc 1 is in terms of these Riemann sums. Okay. Yeah. Okay, so now okay, finally after all this preview, I can tell you what we're headed towards. So basically, the problem that we want to discuss. Um, well, I might as well show you my piece of bread. So okay, so this is like the thing that we want to do now. So basically, you have a function of two variables, right? If you have a function of two variables, then the graph looks like a surface. Uh, well, this is not real bread, right? I got it on Amazon. But the graph of a function of two variables looks like a surface, which you can think of the top of this loaf of bread. Um, and if you have like the analog of an interval, it's a rectangle, right? So if you have you can kind of like ask for the volume between the graph and the rectangle, and that is actually what a double integral is supposed to give as a first approximation. So the double integral is going to be, I'm about to draw a picture in a moment, but a double integral is going to be the volume between the graph of a function of two variables and a region on the xy plane. Okay, so let me show you that next. So what is going to be a double integral? So what is a so as I was saying, the idea is that if you have the graph of a function of two variables, if you have the graph of a function of two variables, the graph is the surface. I'm trying to draw it up. I'm trying to draw, it looks like a bit flat, but it doesn't have to be flat or anything. Like it's just like for purposes of my picture that is easier for me to draw. But like the graph is a surface. And the idea is that if, for example, I have a rectangle, so R here is a rectangle on the plane. Then you can kind of like look at the volume between the graph and the rectangle. So let me see if I can draw that here. So you have to imagine that kind of like the rectangle. You have to imagine that in a sense, kind of like the rectangle traps part of the graph. Wait, let's see. And so there is a volume. If I color it, it would be too chaotic, but I'll show you an animation on GeoGebra in a moment. But there's kind of like a volume between the graph of the function and the rectangle. Well, net volume, in fact, because if the graph happens to be under the xy plane, it would count negative, but that's a little bit too hard for me to draw. But so there's kind of like a net volume between the graph of z equals f of xy and the rectangle on the plane. And the idea is that the double integral is supposed to compute this quantity. So the double integral I'll show you, I'll kind of like mention some of the notation now. So the way we will write this down, and I'll explain kind of like what I'll do today is explain how you're supposed to find these quantities. But but you know, the idea is that you would refer to this in this way. So you would write. So this is what we are supposed to try to find today. So this is going to be the usual way in which we will write the double integral. So again, this will represent, this represents f of xy over the rectangle R. So the way I'm writing it, hopefully it's kind of like conveying. I'm using two integration symbols, right? Two integral symbols. So essentially what will happen, and I'll show you in a moment what the idea is, but what will happen is that you know, you will have to do two integrations. So one for x and the other for y, or one for y and the other for x. So basically, what will this will amount to is that we will integrate, you know, we will integrate with respect to x and with respect to y. Okay. Is that making sense so far? So good. Any questions about this? How are we doing? Anyone? Okay, so before we get into the details of how this integral is going to take place, let me just show you that there is kind of like a Riemann sum thing that you can do in this situation as well. So you can also find this integral. So I'll show you that first, and then I'll tell you in practice how we will compute this. So what's happening here? Let me just. Actually, this animation is pretty nice. Like I've never seen it before, but this actually is pretty good one. But first, like what you can see here, this is a good example of how this is supposed to look like, because here, like the red part is kind of like the graph, right? And then you have a rectangle, right? The rectangle you can kind of like see from here, from this perspective. So there is kind of like a volume that's trapped. There is a volume that gets trapped between the graph and the rectangle, right? And that is essentially what the double integral is supposed to find. Okay, so this is what the double integral is going to try to find for us. So I'll take a picture of this one because I kind of like it. So in this case, like the rectangle is determined by x being, if you can kind of like see it here, x is between -1 and 1, and y is between -2 and 2.09 for. But you could use other rectangles. Let's see if this actually works nice. Well, let's actually do 1.5. And then let's do. Right. So again, like with a different rectangle, I now chose a different rectangle, and there's like a new solid that gets created um, between the graph and the rectangle. Okay. Now, what I was saying, let me just see if I can find this one. Right. What I was saying is that just as in the case of Calc 1, right? Just as in the case of Calc 1, if you have the graph, one way to approximate the volume, right? It's kind of like using like now kind of like more like boxes or prisms, which is how they're being called here in this animation. Um, and the more that you have, the better approximation this would be to kind of like the volume that you're seeking. So here you can kind of like see that if you increase the number of cubes or like, well, not cubes because they don't have this, you know, let's just call them like prisms. If you increase the number of prisms or boxes, the smaller that they are, the better approximation it is to the volume. Okay, so all that I'm saying is that just as in Calc 1, there is kind of like a Riemann sum type thing that you can do here for these integrals, and so this double integral in reality is defined as a limit of Riemann sums. So I'll take a picture of this one as well. Okay, so essentially what I'm trying to say is that in practice, like these integrals are defined. These double integrals, just to emphasize that I'm talking about the double integrals. Okay, so these double integrals are defined using a Riemann sum. But just as in Calc 1, we won't find them in that way. That's kind of like the definition. But in practice, this is not the way we will find the integrals. We'll do it in a different way. Okay. Is that okay? Some making sense so far so good. Any questions about this up to now? Is that okay? Okay, so now what I'm going to tell you is how we are going to find them. Okay, now this is where I need to bring my props. So give me a second. I'll bring some burger buns. You'll see what I'm going to do in a moment. Okay, uh, perfect. So let's do this. Can everyone see my camera, by the way? I think you see me. Okay, good. Okay. So my again is an advantage of doing this in the house is like I can just use kitchen props. So this is just a piece of bread. Okay. Well, half of a hamburger bun. Okay. So you can see it there, right? So the double integral again. if you think of the top, if you think of the top of the piece of bread, of the burger bun, that is kind of like the graph of the function of two variables. Okay. Uh, and so uh, the volume that the volume of the solid is what the double integral is supposed to compute. Okay. Now, what I'm going to use is kind of like the principle. Now I'm just going to use the principle that the bread, it's kind of like a principle of conservation of mass or conservation of bread, if you want to see it that way. That um that I can slice. Let me see if I can do this like a bit more. Let's see. Okay, so the idea is that I can slice a piece of bread in two different ways, which I'm about to show you what they are. So let me see if this kind of like looks fine. Okay, there you are. Now you go. Okay, so I'm going to make cuts on this piece of bread in two different ways. Okay, and I'll show you what that means in a moment. So you can cut this in this way. So I'm cutting the bread into mini slices, right? So I'm cutting the bread into mini slices. But the idea is that if you put all these slices back together, right, you do recover the original piece of bread, right? So that's what I meant by conservation of volume, right? That you can cut the bread into mini chunks of bread, and if you put them back together, if you imagine you could glue them, you would get the original bread again. Okay. So if you notice what I did, right, the way I was cutting it is kind of like I was cutting it this way. Okay. Okay. Now, but this is like you can cut a bread in many different ways. This is not the only way you could cut a bread, right? So let me see if I can put this here. So let me just take another like brand new bread slice, right? And so instead of cutting it this way, which is what I was doing before, I'll cut it in this other way. So I'll cut it in this other way. So if I cut it this way, I get these other bread slices. Okay. So you get these new bread slices. And again, if you separate them, but were to put them back together again, that would recover the entire piece of, the burger bun or half the burger bun, right? So my point of, I can put like the two cuts like side by side, I guess. Um, Well, okay, I don't think I'm reconstructing the bread in the best of ways, but hopefully you kind of get where I'm going with. So the point that I'm trying to make is that if you have like a physical object like a bread, you can cut it in different ways, but the different ways of cutting it shouldn't affect the different ways of cutting it, like that shouldn't affect the volume of the solid, right? Like the solid has a volume that's kind of like an actual property of the solid, and you can just use different ways to kind of like cut it, right? But again, that is it is up to you. What I'm trying to say is that it is up to you how you choose to cut it down. Okay, is that kind of like making sense? That everyone agrees? Is that okay? Now, why is that useful for our purposes? Because kind of like the two different ways that I was showing you of cutting the bread, that corresponds. I'll show you a nicer animation in a moment, but that corresponds to integrating the function first with respect to one with the variable x, for example, and then y, or integrating first with respect to the variable y and then x. So the point is that the two methods that I show you for cutting this corresponds to two different ways you could integrate the function. So the idea is that because the function depends on two variables, you can integrate either with respect to y or with respect to x. You have to integrate with respect to both, but the idea is that the idea is that it won't matter which one you do integrate with respect to with first, because it's kind of like analogous to this fact that I just showed you with the bread, that you can cut it in different ways and it still recovers the same volume. Okay, so essentially that is what will happen in a moment. Let me just return this bread back to the kitchen, and then I'll be back right back. Ah, okay, so yeah, what I was saying, just to kind of like, let me show you an animation first of what I was saying, just to make it a bit more clear. So essentially, what you're seeing, basically, what I was doing with the bread is a version of what's happening here. So here you have a solid, sorry, you have a graph, right? The graph is kind of like similar to the burger bun, the top of the burger bun. Um, and there's a volume between the graph and a rectangle, which is this rectangle that you see on the XY plane. So basically, you can come in with your knife and you start making cuts. It's kind of like these magician shows where they kind of like cut a person, cut in quotes. So you get what you may call like a slice or a cross section. Okay, so you get a slice like this, which is shown in yellow on this animation. And the idea is that you should imagine that this slice is just kind of like in this mindset of calculus is very, 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 very thin. So it almost has no thickness. It almost has no thickness, or you could say that it's infinitesimally thick if you want. Because if it's super, super thin, basically on one of these slides, that's what it happens is that only one of the two variables changes at a time. So essentially, when you do it that way, you're kind of like holding constant the value of one of the variables. Um, and as you move that slices, as you move the place where you're making the cuts, you get kind of like the different slices or the different cross sections. And the idea is that if you put them all together, that gives you back the solid. Okay. But the way I want you to think about this problem is that kind of like the slices are very thin, or these cross sections are very thin, because if they're super thin, if they're really thin, then only one of the variables is changing. So here, the way this animation is working, um, they kind of like set constant the value for y first. So for example, this cross section has value of y set equal to 1 first. So that means that x is changing first. And so basically what that amounts to, and I'll write this down in a moment, what this amounts to is that you integrate first with respect to x. You would integrate first with respect to x, and then as you move the cut, where you're making the cut, that corresponds to integrating with respect to y. So that's how the double integral would be set up in this case. But kind of what I was telling you about earlier, again with the burger bun, is that you can kind of like make the cut in the opposite order. So you see, like now I changed how the cuts look like. So if you cut it this way, the idea is, again, if the cuts are super thin, only one variable is changing. And so like you integrate first with respect to one of the variable that's changing on one of these cross sections, and then to recover the full solid, you can like integrate with respect to the remaining variable second. So here, what they're fixing first is the value for x. So they're fixing the value for x, and that what that means is that y is changing first. So that's why if you see this order here, and I'll explain this in a moment, but this is being integrated first with respect to y, because y is a variable that's changing, and then what you get, you integrate with respect to x. So this doing the integration this way is called iterated integrals, because basically you're breaking up the double integral into two mini integrals, one with respect to each of the variables. So let me put the pictures here. And okay, and then I'll do like a quick example, and that's kind of like the last thing I'll do for today. And then next time on Thursday, what we will do is kind of discuss like more complicated shapes. Right, but the key inside again is that if you make a very thin cut, if you make a very thin cut or cross section, then one of the variables is kind of like kept constant. And so what that amounts to is that you end up integrating first with respect to one of the variables, and then with respect to the other one. Okay. So essentially what this means is that for us, the problem of doing the double integral will become a problem of doing two integrations. So so in practice, okay. So hopefully this reminds you of partial derivatives. That's a good analogy to have in mind, because when we were doing partial derivatives, you would set one of the function equal to a constant. So one of the variables equal to a constant, right? Um, so this should remind you. Like, I'll make another remark. This should remind you of partial derivatives, where to find these, you set one of the variables equal to a constant. Okay. Um, and in fact, not that anyone called them like this, but basically what we're going to do is kind of like partial integrals. That's one way to think about it. So we are going to be doing. But again, they get called iterated integrals, which are known as. Okay. Is that okay? Is that making sense? How are we doing? Okay, so let me again. I'll do an example for today, and then next time I'll do more complicated situations. But okay, here's an example of what we're trying to do. So let's say you want to integrate. I'll give you a very simple function of two variables. So my function is going to be, the function of x and y is going to be x squared times y over the rectangle. So let's say x is going from 0 to 3, and I'll make y and y is going from 2 to 4. Okay. Okay, so here I will try to do like a fake picture because this is too hard. You don't have to do like the 3D solid in practice, but I'll just try to do an attempt of that, like because it's the first time we're doing this. So the idea here is that you have the graph. By the way, this is not how the graph looks like. Again, I cannot draw anything too accurate because otherwise, like the picture looks like a bit messy. But this is the graph of x squared y, like again a fake graph because that's not the actual picture. I'm just trying to do something that kind of like represents like the situation, and then you have a rectangle where x goes from 0 to 3, and y goes from 2 to 4. So x goes from 0 to 3, and y goes from 2 to 4. So the rectangle kind of like looks something like that. Okay, so that's kind of like how the picture is in this situation. And again, what we're trying to do is kind of like we're going to do the volume of this solid. So again, I'm going to try to draw like kind of like a fake picture. But you have to imagine that there's some sort of box there, and we're trying to find well, box in quotes because it can be like it doesn't have to be like rectangular. It's kind of like a deformed box, kind of like similar to my bread. You can kind of like squash it, and then like it's a little bit more deformed, right? It doesn't have to be flat at the top, you know. So we want to find the volume of this solid. Hmm. Is that okay? Is that making sense? Uh, Okay, so the idea here is that again, what I have been trying to tell you is that you have two ways to slice this up. So there are two ways to slice it up. So the first way to slice this up, first way to slice this up is what I'm about to draw here. So basically, You make a cut where you kind of like fix the value for x, which is kind of like this green cut. Okay, and that gives you like a cross section in here. So the idea is that along this cut, on this particular cut, the variable that's changing is y. So let me write this down. The variable that is changing is y. So what that amounts to is that you will integrate this first with respect to y, and then what you get, you will integrate with respect to x. So in practice, what this means, we will integrate first with respect to y, and what we get and what we obtain will be integrated. Okay. So this is going to be called, I'll write it down on the next page, but this is going to be called the order of integration dy dx, because first you're going to integrate with respect to y. So this is called the order of integration. Okay, so how does that look in practice? So you had the function. So our function was x squared y, okay? And the idea is that you have to you are going to integrate first with respect to y. So I'll put here y first. It's kind of like an integral inside the other. That's how you should think about this. Okay. So that's why I'm putting these parentheses to kind of like emphasize this, which you don't end up doing it later on. But to have the parentheses is useful at the beginning. So y goes from 2 to 4, right? Because those were the values for y on this rectangle. Oh my god, it went upstairs to the tank. And then what you get, you will integrate with respect to x. And x for this rectangle went from 0 to 3. Is that okay? Is that making sense? So the way we are going to do this integral is that you pretend, because this is an integration first with respect to y, you pretend that x is constant. So you see it's similar to these partial derivatives that I was telling you about. So since you're integrating first with respect to x, you pretend, sorry, with respect to y, you treat x as a constant. And that's the only thing you have to remember. Like everything else works exactly the same way as in Calc 1. I think my video is frozen. Let's see. Okay, now I'm back to normal. Um, so it is like the nice thing about this, that you are not going to learn any new ways of integrating things. Because you're just going to integrate like as in Calc 1. You just have to keep in mind which variable is being treated as a constant for the time being. Okay, that's the only thing you have to remember. So here, if we're integrating first with respect to y, it's kind of like doing y dy times a constant, right? Because x squared is like a constant. So it's similar to that if you had like pi squared y. If needed, you can always like mentally put like replace x with pi or something like that, just to kind of like remember that it's supposed to be treated as a constant. So what is the integral of y with respect to y? That's just y squared over 2. So these just, by the way, since this is uses two variables, it's useful to put the bounds specifying which bound for which variable the bounds are referring to. So here, like the bounds refer to y. So that's why I'm putting y equals 2 and y equals 4. But all that I'm saying is that you put x squared, y squared over 2. Oh my god, I hate this autocorrect sometimes. Okay, so annoying. Okay, so these will be evaluated at y equals 4 and y equals 2. And after you finish doing the evaluation, that's when you integrate with respect to x, but only after you finished evaluating. So that's why I'm not adding the constant of integration, because these integrals are always going to be definite integrals. So, you know, you don't need the constant of integration. Is that okay? Is that making sense? Sorry, and then the rest is I still need the dx. There's still like a dx. Okay, so let's just evaluate this. Y equals 4. Y squared becomes 4 squared, which is 16, right? So you get x squared times 16, right? Minus x squared over 2 times 2 squared, which is 4, right? And all of these gets integrated with respect to x, which of course you can simplify a little bit before doing the integral. So 16 over 2 is 8, and 4 over 2 is 2, right? So you're doing 8 minus 2, which is 6. So this is going to be the integral from 0 to 3. And then again, this is kind of like an ordinary integral, what you have to do. So what's the integral of 6x squared dx? That's 6x cubed over 3. And you evaluate it at the bounds. Right. And so, well, only the one with x equals 3 survives, because with 0 you don't get anything. But let's just do it quickly. So you get 6 over 3 is 2. So you get 2 times 3 cubed minus 2 times 0 cubed. And what does that give you? 3 cubed is 27. 27 times 2 is 54, right? So the volume for this solid over this rectangle would be 54. Is that making sense? Any questions up to this point? Anyone? I don't know. Well, actually, that's what I was going to do next. That you can actually flip it around and you can do x first on the inside, but it will have the same answer. That's kind of if you remember the burger buns, that corresponds to the two different ways in which I cut it. Yeah, 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 yeah. Of course, it's not that you have to do it. Exactly, exactly. I will do more complicated examples next time. It's not that you are going to be asked to do it both ways. It's more that sometimes one way is more convenient than the other. Right now, because we're dealing with rectangles, there's really not much of a difference, but you'll see that on Thursday. There are times when one order of integration, which is how you would call this, is significantly friendlier than the other one. So it can get pretty nasty, but kind of like, but in principle, they would give you the same answer. It's just sometimes one is not as practical as the other to implement. But here with rectangles, there's really not much of a difference that you can tell. You have to wait until like the examples on Thursday where I'll show you uh, some of the differences. But yeah, like that's kind of like the idea that you have to remember that you can slice the bread in different ways, and it still gives you the same result. And in polar coordinates, what will happen when we talk about polar is that you kind of like slice it more like a pizza pie, right? Because when you cut a pizza pie, you don't cut it in rectangles, right? Like everyone kind of like cuts them like using rays from the origin. So that is the only difference. Like it really doing different coordinates corresponds to cutting the solid in different ways. That's kind of like how you can think about that. Well, let me do the next. I'll just do it in the opposite order so that you see that it does give you the same answer. It's like and I still have enough time. So, but yeah, like the idea is that the other cut goes like this, And if you cut it that way, now as you can tell, X is changing first. If you just focus on this purple segment, along this purple segment, X is changing first. So along this segment. So basically what that amounts to is that we're going to integrate first with respect to X and then with respect to Y. So it's essentially the same idea, you know, you put X squared Y, but now with respect to X. And so because it with respect to X, you have to put the X bounds first because now you're integrating first with respect to X. So X goes from 0 to 3. And then with respect to Y, Y would be the other variable of integration. So, and Y goes from 2 to 4, just as before. But yeah, the idea here is that you pretend now, because you're integrating first with respect to X, you pretend that Y is constant. So since now, you treat Y as a constant. Okay. So nothing else changes. So it's kind of it's like it's just kind of like a partial integral with respect to X. That's one way to think about it. So Y is now like the constant. So you're just integrating X squared with respect to X. That's X cubed over 3, right? And the idea is that after you evaluate, then you integrate what you are left with respect to Y. Okay, but you evaluate first and then do the integration. Okay. So let's just do this quickly. So you put X equals 3, so that gives you 27 over 3 times Y minus 0 cubed over 3 times Y, which of course you don't see that, but I'm just writing everything so that you can see it, right? And so that gives you 9Y. Right, and now this is like an ordinary integral of one, with respect to Y, so that's 9Y squared over 2. And evaluated at Y equals 2 and Y equals 4. Okay. And so that gives you Y squared, which is 16, right? Minus Y over 2 times 4. Okay. So that gives you 8. Okay, so that gives you 9 times 8 minus 2. So that's 9 times 6. And that is 54. Which, if you remember, that is the same number that we had before. Like, if I can go up for a second just to show you. If you go to the previous page, we had also found 54 before, which is supposed to happen, right? It's not a coincidence. This will always be true. So the idea is that you get the same answer as should be the case. So you get the same value. Okay, but it kind of like it's being found in different ways because again, each way of integrating corresponds to a different way in which you could cut up the solid. So that it does have kind of like the origins for each value are different because it corresponds to, one way you're cutting it like this and the other way you're cutting it like this. So it does correspond to different um, ways. Is that making sense? Anyone? Okay, so we'll continue talking more about this on Thursday. But yeah, this I think is a good place to end. I'll send you the link to the video recording in case you want to watch it. I'll send the notes as well. Also, once we're done with the class. But yeah, I'm pretty sure I'll be fine like by Thursday. So I'll see you on Thursday in person. But yeah, I needed to recover today. Yes, Thursday of next week. Yes. Thank you. Thank you. Thanks.